So far we've talked about the impact of magnetic fields, the forces on charged particles. Now we're going to talk about what actually causes magnetic fields, what creates them. And I hope it won't be a surprise to you to learn that they're created by charges, and in fact moving charges, since the forces are on moving charges. So we talk about the cause of a magnetic field being a current. So if we have a wire like this that's carrying a current in that direction, we can talk about the magnetic field at a point. So I'm going to pick a point right here, a point P as usual, and we can look at the magnetic field due to some little bit of current that's in that little area, that's in a little dl, a small length of the wire. So we have a current I that is in that direction, and we can say what is the magnetic field at this point that is a distance r away. And the magnetic field, the small contribution from this little this little bit of current, this little dl, here's our r hat direction, that's the direction to the point, and dl points like that, is given by the Biot-Savart Law. Okay, and so that says this little bit of magnetic field at this point is equal to mu naught, which is a constant, over 4 pi, times I dl cross r hat over r squared. So mu naught is given by 4 pi times 10 to the minus 7. And then we need to look at the units of this. So let's stop for just a minute and look at that. So what we have is that has a unit of amps. This has a unit of length, because once we integrate over the length, that'll be length. This has a unit of length, right? Length squared. And of course, this needs to be in Tesla. So that means the units of this need to be Tesla, so that I'm left with Tesla there, times a meter, because I've got a meter squared in the denominator and a meter in the numerator from that, divided by amps. Okay, so that is our value of this constant, our mu naught. So we can plug that in. What we want to do right now is look at the direction of things. So if we look at this, I've got, just sort of zooming in on here, I have dl going sort of up and r hat in that direction. So I'm going to use my right-hand rule, and I'll find that the direction of dl cross r, okay, so this might be my angle theta, in there, we can say that dl cross r hat is just our, sorry, let me move that down. Our r hat is just a unit vector, it just tells us a direction, so it has a length of 1. So that is dl times the sine of the angle between them. Sorry, I wrote that as a theta. So sine theta, that's the magnitude of this, and then the direction comes from using our right-hand rule from the cross product. So in this case, that would be into the page. So that would be sort of the direction of our dB. So I would set up sort of an axis like this. That's, and let's say there's our dl sort of axis. So dB is along this into the page direction. Okay? And you can rewrite if you want. There's your r hat, and there's your dl. That little bit of length that points in that direction. So that would be the contribution to the magnetic field for this point. Of course, we have a point over here that contributes, and we have points over here, a little dl along here that contributes. And notice this is going to have a different r value, and we have to do the cross product for all of these. So to find the overall magnetic field, we say our magnetic field B is equal to this integral dB, and it's really kind of a messy integral to do. Most of the time, we really can't easily do this. This would be I dl cross r hat Notice that r hat direction is going to be changing, so sine of theta is going to be changing, all of those things. R squared is going to be changing, and then we have to add up all the dl contributions. So in general, we'd rather not do that. And so we're going to move fairly quickly to how we can avoid that. But I'm going to give you one instance where we can do this fairly easily. And that is if we have a loop. And this is pretty important because we think of permanent magnets as sort of due to the orbit of the electron. So if we think of an electron or a charge going in a perfect circle, okay, so we think of it as due to the orbit of the electron, but also the spin of the electron. So we think about a little tiny current going around like this. So if we have a current, so here's my current going around in a circle like that, then this is my, and I want to find the magnetic field right here in the center. So there's my point P. Then in this case, notice that I have like my dl is like that, my r hat is in that direction, so dl cross r gives me something that's out of the page. So my magnetic field is coming out of the page here. Again, if we set up an axis where this is coming out of the page. So that's from my right-hand rule, my dl cross r. The b is out of the page. So I can say db is equal to mu naught over 4 pi I dl cross r. Those are at right angles, so that would be times sine of 90 degrees, all over r squared, which would be the radius. So if this is a radius, capital R, so we say this distance here is capital R. Then, and then this, we know the direction would be out of the page. Out of page is sort of my vector direction. Vector hat, that's my direction if you like, which we could set up an axis, like call that z hat or direction. But anyway, so the magnitude is given by this, and then the direction would be given by out of the page. So we'll write it like that. That's our direction. And so to find this integral, we would say b is equal to this integral db. And in this case, this is not a very hard integral to do. This is mu naught over 4 pi. The I is a constant. Sine of 90 degrees, it's always 90 degrees. It doesn't matter where I set up my dl. If I set up my dl here, my r hat is still in this direction, so it's 90 degrees because we picked a circle. And so that sine of 90 is equal to 1 r, and then we've got dl, and we have this integral, and we can look at all the constants. And in this case, notice that all of these are constants, so this is a really easy integral to do. So my magnetic field is just mu naught I over 4 pi, sorry, that's an r squared. Somehow didn't keep my squared, so r squared. And then this integral of dl, which is just the length of the wire, so that would be the length of the wire. And the length of the wire is just a circle. It's the circumference of a circle, so that would be 2 pi times r. And so this magnetic field right in the center, and only in the center, is mu naught I times 2 pi r, all over 4 pi r squared. Those give me a 2, and that cancels, and so this magnetic field just becomes mu naught I over 2r. And this is really the easiest case to do, which is why I did it for you, because what I want to do is make the same claim that we did when we were looking at electric fields, which is we can find the electric field by doing the integral, right? So when we were on electric fields, when we had electric fields, we said our dE was equal to k dq over r squared, that, and then we had to have plus the direction, whatever that was, right, the direction that a positive charge would feel. And we had to integrate up over all these charges. We added them along a wire, for example. This is the one we did in class, right? We had a little dq here, and we wanted to find like the magnetic the electric field at that point, so we figured out the direction was that way. That was the direction of dE. And then we had to add up all of these contributions. And what you discovered is that you'd really rather not do that. And so we went to Gauss's law. And so Gauss's law was good for certain symmetry. So again, this is the electric field case. Gauss's law, if you recall, was E dot dA is equal to Q enclosed over epsilon naught. Now this was always true. It's only useful for certain cases where we can pull the electric field out of this interval, where we can do the dot product and we can get rid of the electric field. But this was on a Gaussian surface. Remember, we drew those mythical Gaussian surfaces. Okay, that was the dA on the Gaussian surface, so that way this enclosed meant something. It was the charge that was inside the surface. So we're going to do something similar. We have a dB expression that's way back over here. That's the Biot-Savart Law. And we'd like to avoid using it. We used it in one case. That's this, the magnetic field in the center of a loop. And that's it. I'm not going to use it for any other case, because we're going to do the equivalent to Gauss's law, except for the magnetic case, it's Ampere's law. But it has the same idea. It says an integral of B dot dl is equal to mu naught times an I enclosed. So again, we're going to have a surface or something, and inside it, this is going to be inside, and we need to have some symmetry for this to be useful. So in this case, we're going to say that we have a long wire of current. Here's my I, current, and again, we want a long wire, just like we did in the electric field case, because we want to have symmetry, so we know the direction of the magnetic field. And instead of a Gaussian surface, what we're going to draw is an Imperium loop, which is what this dl is about. It's about a length of a loop. So for this setup, our Imperium loop is going to look something like this. Again, it's centered on the object, so we can take advantage of the symmetry. So everywhere is the same distance r away. So this is our Imperium loop here that is size r, and we pick the r for finding the magnetic field that we want. So again, we're trying to find the magnetic field, say, right here, or maybe right here, somewhere a distance r away. And so we want to then find our magnetic field a distance r away, so that's how we draw our Imperium loop. So when we do this, we're going to set up, first of all, the current enclosed is whatever this current is. This is the easy, let's say that's 3 amps. That's how much current is enclosed, so the right-hand side is just mu naught times 3 amps. Okay. The magnetic field. Well, first we need to find the direction and sort of make the case that this is the right symmetry. So if we look at Ampere's law, then here's my I. This is my little dl, for example. Here, my r hat is like this, out to this point, for example. Then dl cross r gives me a magnetic field, a little dB that's in that direction. If I look over here, it turns out it's in this direction. Do check it. And so what we get is we get a different, a new, that's easier right-hand rule. It's connected to our cross-product right-hand rule, but this is a little easier. This is the right-hand right rule. Let's try that again. Right-hand rule. And this right-hand rule says that we put our thumb in the direction of the current of pi, so of our right hand, our thumb in the direction of the current, so in this case up, and then our fingers curl around, the curling of the fingers, curl of fingers, give us the direction of the magnetic field. So it's sort of the curling around right-hand rule. So if you look, this is a picture from your book that shows the direction of the magnetic field. This is the right-hand rule with the thumb in the direction of the current here, right? And then the magnetic field looping around the wires like that. So that's your right-hand rule, the curling right-hand rule. So the thumb points in this direction up here, and then as you rotate your hand around, it rotates, it looks like that. And so behind the wire, it goes up like that. In front of the wire, it looks like that. So that's your curling right-hand rule for wires. And so that's a really convenient right-hand rule for finding the direction of the magnetic field. I think it's easier than doing your cross product using the Biot-Savart law. So if we use the curling right-hand rule, you can check that the magnetic field points in this direction all the way around. And since we're the same distance away, notice I'm going to start looking at this left-hand side of the equation. And so I've got, of my Ampere's law equation, that's my whole Ampere's law equation. So I've got B times dl, so dl is a little piece of the loop. Okay, so now it's a little piece of the loop, a little length of the loop, times the cosine of the angle between the magnetic field and this dl. So if we look at this, dl is a little piece of the loop, db, or b, is in that same direction. So my angle between these two, cosine, would be cosine of 0 degrees, which is a 1. And that, the left-hand side, okay, so I've got this integral, is equal to mu naught 3 amps. And just like Gauss's law, this is only useful if I can pull this magnetic field out of the integral, if it's constant. So what we do is now we're looking at the magnitude, and we can say that even though the direction changes all the way around the loop, we've gotten rid of the vector part because we've done this dot product, that the magnitude of this B doesn't change. It's a constant value of our B. So in fact, we can say that, whoops, our B is a constant value along this loop. And it's going to be the same value everywhere because we are the same distance away. If we go back to the Biot-Savart, the magnetic field depends on the current, and it also depends on how far you are away from the current. Well, if you're the same distance away, if you've got this r squared is the same distance away, you're going to have the same magnetic field if everything else is constant. So in fact, this does have a constant value, and so we can pull that out. And so I've got B, the integral of dl, is equal to mu naught times 3 amps. And so this dl is just, the integral of dl is just whatever the length is. So this is B times the length equals mu naught A. Now, in this case, we are doing this integral along the Amperian loop, not the length of the wire, but along our loop. So this now becomes the length of the loop. And this is a circumference of a circle. So that's equal to 2 pi times r, however long, however big this radius is wherever we put this loop. And so then our magnetic field is equal to, well, let's write that in first. Magnetic field times 2 pi r is equal to mu naught times the current, in this case 3 amps, but it could be whatever we had, where the magnetic field is mu naught times 3 amps over 2 pi r. So that determines our magnetic field some distance away from our long wire. Okay, so to sum up the magnetic fields that we found 2 different magnetic fields. We found the magnetic field from a long wire like this, if we're a distance r away, like at this point right here, that magnetic field is equal to mu naught times whatever this current is, times 2 pi over r, where r is the distance, this radius, out to this point. Okay? The other current that we found, and the direction is given by that, the other magnetic field that we found, and these can kind of get confused, is if I have current in a wire like this, there's my current, I can use my curling right-hand rule. In this case, I find the magnetic field that's coming out of the page in the middle. In fact, the magnetic field sort of does this kind of a thing. That's my magnetic field, comes out, goes out like that, and goes in, goes out. Ooh, that's not very pretty. Goes in like that, okay? So that's the magnetic field, but right in the center, and only in the center, we say that our magnetic field, if we go back up here and see what we got from our integral, is given by this expression right here, this one, mu naught I over 2r, where this r is the distance to the center. Okay, so we've got two different expressions. They look very similar, and so I just wanted to have them both out in front of you so you can see the difference. This one we can adjust by how far away we are from the wire. This one is only good at the center of a loop. And if we go off center, along the axis or even on the outside, the field drops off from there.